Tonight, if the sky is clear and you know where to search, you will spot a faint, rusty glow among the stars. It does not twinkle quite like the others. That steady, amber light is Mars, our celestial neighbor. For millennia, humans have stared at that wandering dot and projected our myths, our ambitions, and our desperate hope for a second home onto its ancient surface. So why haven't we gone? And for those brave enough to volunteer for the journey, how long would it actually take to arrive, explore, and return home safely? The answer is far more complicated than most people realize. Are you ready? Let's begin. When we imagine traveling here on Earth, we instinctively think in straight lines. You cannot aim your spacecraft directly at Mars, ignite the thrusters, and coast there in a straight trajectory. If you attempted that, by the time you crossed the gulf of emptiness between worlds, Mars would have vanished from that spot. It would have continued its endless orbit around the Sun. You would drift alone through the void, a frozen monument to miscalculation. Every object in our solar system is perpetually in motion. Earth hurtles around the Sun at roughly 107,000 kilometers per hour. Mars travels its own orbital path at about 86,000 kilometers per hour. The Sun's gravity tugs on everything. To successfully reach Mars, you must abandon the mindset of a driver on a highway and adopt the mentality of a quarterback throwing a football. A skilled quarterback never throws toward where the receiver currently stands. They throw toward where the receiver will be when the ball arrives. They lead the target. Interplanetary navigation is the ultimate exercise in leading your target, except your target races through space at tens of thousands of kilometers per hour, and your ball requires months to complete its arc. We are not aiming at a stationary destination. We are predicting a future rendezvous point where our spacecraft's curving trajectory will intersect precisely with Mars' orbit at the exact instant Mars arrives there. This demands flawless mathematical precision. An error of a fraction of a degree means missing the entire planet by millions of kilometers with no opportunity to course correct. The fundamental obstacle is the staggering emptiness of our solar system. Those tidy diagrams in textbooks showing planets arranged like marbles on a shelf? They deceive us for the sake of fitting on a page. Reality is overwhelmingly vacant. The Moon orbits approximately 384,000 kilometers from Earth. That is considerable. The Apollo astronauts needed roughly 3 days to traverse that distance. But Mars exists on an entirely different scale of remoteness. Because both Earth and Mars circle the Sun at distinct velocities and varying distances, the chasm between them fluctuates constantly. At their closest possible approach, a rare event, Mars hovers around 55 million kilometers away. That is already over 140 times more distant than the Moon. However, when both planets occupy opposite sides of their orbits, separated by the Sun itself, that gap balloons to approximately 400 million kilometers. This is emptiness so vast that our minds struggle to genuinely grasp it. We cannot simply launch whenever ambition strikes. We are prisoners of celestial geometry. We must wait for Earth and Mars to align in precisely the correct configuration to make the voyage feasible with the propellant we can carry. If this deep dive into the realities of interplanetary travel resonates with you, please consider tapping the subscribe button and leaving a like. It signals to the algorithm that this content matters, and it genuinely helps me continue producing these explorations of our cosmos. This critical alignment, when both worlds position themselves for the most efficient transfer, occurs only once every 26 months. That is the rhythm we are bound to. Every 2 years and 2 months, a launch window opens for several weeks, then seals shut for another lengthy cycle. This timetable dictates every aspect of Mars mission planning. You are not merely scheduling a trip, you are synchronizing with an immutable cosmic calendar. Assume we have waited patiently for this window. The planets are sliding into position. We have constructed an enormous rocket, something rivaling the legendary Saturn V, that carried astronauts to the Moon, or the Starship currently undergoing testing in South Texas. We launch, we claw free of Earth's gravitational embrace, the most energy-intensive phase of the entire expedition. Now we coast through the darkness. How many days, weeks, or months pass before the rust-colored terrain of Mars fills our viewports? With contemporary propulsion, chemical rockets burning liquid oxygen mixed with methane or hydrogen, we cannot maintain continuous thrust throughout the voyage. We ignite engines fiercely at departure to accumulate velocity, coast for millions of kilometers, then burn hard again upon arrival to decelerate and avoid overshooting our destination entirely. The most fuel-efficient trajectory, the one permitting us to transport sufficient cargo and crew to survive, is called a Hohmann transfer orbit. It traces a long, elliptical arc around the Sun, gradually nudging the spacecraft from Earth's orbital path outward to intersect with Mars' orbit. Following this energy-conserving cosmic highway, the one-way journey to Mars spans approximately 6 to 9 months. Absorb that for a moment. Not days, not weeks, months. Under optimal conditions, you are looking at roughly 180 days. Under less favorable circumstances, closer to 270 days. And that is merely to arrive. Picture spending 7 or 8 months confined within a habitat smaller than a modest apartment, sharing every moment with 3 or 4 crewmates. No fresh breeze, no windows you can open, a constant mechanical hum from life support systems keeping you breathing. Beyond the hull lies only the blinding sun and the relentless, invisible radiation of deep space. Each day mirrors the previous one. Earth gradually shrinks until it becomes merely a bright, blue-white speck, indistinguishable to the unaided eye from countless other stars. You are profoundly isolated in the void. This transit duration is precisely why sending humans to Mars proves exponentially more challenging than lunar missions. The Apollo expeditions were sprints, roughly a week from launch to splashdown. Almost anyone can endure a week of discomfort. Long-term radiation exposure, severe muscular deterioration, psychological fractures, these concerns remain manageable over 7 days. But 9 months? 9 months constitutes a marathon through an environment actively hostile to human survival. During that crossing, the human body rebels against weightlessness. Bones begin leaching calcium, growing brittle and fragile. The heart, no longer laboring against gravity to circulate blood upward, gradually reshapes and weakens. Eyeballs can deform under altered fluid pressures, potentially causing permanent vision damage. Then there is radiation. Beyond Earth's protective magnetic shield, you are constantly bombarded by high-energy particles erupting from the Sun and galactic cosmic rays streaming inward from stellar explosions scattered across the Milky Way. This is not comparable to an extradental X-ray. This represents a slow, accumulating dose that substantially elevates lifetime cancer risk and can trigger acute radiation sickness if a powerful solar flare erupts mid-transit. Engineers must design vessels with heavily shielded storm shelters, compartments lined with water or specialized polymers to protect crews during solar events. Exercise protocols consuming hours daily become mandatory simply to slow the degradation of muscle and bone. Transit time is not merely a scheduling inconvenience, it represents the central challenge of preserving human cargo long enough for them to actually set foot on Martian soil. And remember, that 6 to 9 month estimate assumes flawless execution. It presumes mid-course corrections perform perfectly. It requires engines to fire precisely when commanded, for exactly the programmed duration. In space, margins for error shrink to almost nothing. A malfunction halfway there could mean drifting past Mars entirely, lost forever in the dark. We frequently encounter bold proclamations from visionaries in the commercial space sector, promising transit times of 3 months or less. I genuinely admire that ambition. Humanity needs dreamers pushing boundaries, but we must also anchor ourselves in the physics we actually understand and the engineering we have genuinely mastered. Those accelerated timelines typically depend on technologies still under development. Nuclear thermal propulsion represents one promising avenue. These systems employ a nuclear reactor to superheat hydrogen gas, expelling it at tremendous velocities. They offer roughly twice the efficiency of our finest chemical rockets. NASA and DARPA were actively developing the Draco program, demonstration rocket for agile cislunar operations, to test such technology in space. However, in mid-2025, DARPA cancelled the project, citing shifting priorities and decreasing launch costs, making alternative approaches more attractive. Still, the underlying physics remains sound. Nuclear thermal engines could potentially reduce Mars transit to 4 or 5 months. But even that represents an extended period exposed to deep space hazards. A recent study published in the journal Scientific Reports in early 2025 examined whether SpaceX's Starship architecture could achieve a 3-month transit to Mars. The analysis suggested that with optimal trajectories and the vehicle's considerable propellant capacity, such timelines might become achievable, though significant engineering hurdles remain. Elon Musk himself stated in mid-2025 that there exists perhaps a 50-50 chance of launching an uncrewed Starship toward Mars by late 2026. The ambition is real, the timeline remains uncertain. So we have established the baseline. Using current chemical propulsion and the energy-efficient Hohmann transfer, reaching Mars requires somewhere between 6 and 9 months of travel through the void. But that is only the first act of this cosmic drama. What happens once you arrive? Here is where the mission architecture becomes truly fascinating and where the constraints of orbital mechanics tighten their grip even further. You see, you cannot simply land on Mars, plant a flag, snap some photographs, and immediately blast off for home. The universe does not permit such convenience. Remember that 26-month cycle we discussed? The alignment of Earth and Mars that opens our launch window? That same celestial geometry dictates when you can return. When your spacecraft reaches Mars, Earth will have continued its own orbital journey. It will no longer be in the right position for a direct return trip. You must wait. You must remain on Mars until the planets realign favorably for the voyage home. And how long does that waiting period last? Approximately 18 months. Let that sink in. After spending up to 9 months traveling to Mars, you then spend a year and a half living on its surface before the cosmic clock permits your departure. This is not optional. This is not a choice mission planners make for the sake of extra science. This is physics. This is gravity. This is the inescapable geometry of 2 worlds dancing around the same star at different tempos. If you attempted to leave Mars before the window opened, you would burn through impossibly vast quantities of fuel, quantities no rocket we can currently envision could carry. So let us assemble the complete picture of a realistic Mars mission using technology within our grasp. First, you wait on Earth for the launch window. Then you spend 6 to 9 months traveling outward. You land and spend approximately 18 months conducting surface operations. Finally, you spend another 6 to 9 months returning home. Add these segments together and the total mission duration stretches to roughly 2.5 to 3 years. 1,000 days, give or take, from the moment you leave Earth until you feel its gravity embrace you once more. 3 years. Consider what that means for a human being. Consider what that means for families left behind. Consider the psychological weight of knowing that for 3 years you exist beyond any possibility of rescue. If something catastrophic happens, a medical emergency, a critical system failure, a structural breach, no one is coming to save you. The fastest rescue mission would take months to even launch, and then months more to arrive. You are utterly, profoundly alone in a way no human being has ever experienced. Speaking of being trapped by cosmic distances, if this idea fascinates you, I made a video exploring why humanity might never travel beyond the moon. It dives deep into the barriers the universe has placed before us, not just to Mars, but to the stars themselves. I will leave a link in the description and in the cards above. It pairs perfectly with what we are discussing today. Now back to our Mars timeline. That 18-month surface stay is not merely a frustrating delay, it is actually an incredible opportunity. 18 months represents an enormous amount of time for scientific exploration. The Apollo astronauts spent mere hours or days on the lunar surface. Mars explorers would have over 500 days. They could traverse hundreds of kilometers, drill deep into the regolith searching for subsurface water ice, deploy seismometers to study Marsquakes, and search for biosignatures that might indicate past or present microbial life. But 18 months also means 18 months of survival. And Mars is not a forgiving host. The average surface temperature hovers around -60 degrees Celsius. During winter near the poles, it plunges below -120 degrees. The atmosphere is 95% carbon dioxide, utterly unbreathable. Atmospheric pressure sits at less than 1% of Earth's sea level, meaning your blood would literally boil if you stepped outside without a pressurized suit. Dust storms can envelop the entire planet for months, blocking sunlight that solar panels desperately need. For 18 months, astronauts must maintain habitats, grow food, recycle water and air, repair equipment with limited spare parts, and manage their own physical and mental health. Any resupply mission from Earth would take 9 months to arrive, assuming one launched immediately when a problem arose. In practice, astronauts must bring everything they need or manufacture it on Mars using local resources. This concept is called In-Situ resource utilization, and it represents one of the most critical technologies we must master before sending humans. The Perseverance rover, which landed on Mars in February of 2021, carried an experiment called MOXIE, the Mars Oxygen In-Situ Resource Utilization Experiment. This small device demonstrated that we can extract oxygen from the Martian atmosphere by splitting carbon dioxide molecules. Over its operational period, MOXIE produced approximately 122 grams of oxygen, enough for a person to breathe for roughly 3 hours. That sounds modest, but it proved the concept works. Scaling this technology to produce enough oxygen for crew breathing and rocket propellant represents a monumental engineering challenge, but the foundation has been laid. Water is another critical resource. We now know that Mars possesses substantial deposits of water ice, particularly near the poles, and buried beneath the surface at mid-latitudes. Orbital observations from spacecraft like the Mars Reconnaissance Orbiter have mapped these deposits in remarkable detail. Future missions could potentially extract this ice, melt it, purify it, and use it for drinking, agriculture, and, crucially, splitting into hydrogen and oxygen for rocket fuel. If we can manufacture propellant on Mars rather than hauling it all the way from Earth, the entire mission architecture becomes dramatically more feasible. But let us return to our timeline and talk about the journey home. After 18 months on the surface, the planets finally align once more. The crew boards their ascent vehicle, lifts off from Mars, and begins the long coast back to Earth. Another 6 to 9 months in the cramped confines of their spacecraft. Another half year of radiation exposure, muscle atrophy, and psychological strain. By the time they reach Earth, their bodies will have spent nearly 3 years in reduced gravity environments. The rehabilitation process could take months or even years. We have some data on long-duration spaceflight from the International Space Station. Astronauts like Scott Kelly and Christina Koch have spent nearly a year in orbit. Russian cosmonauts have logged even longer stays. Valery Polyakov holds the record at 437 consecutive days aboard the Mir space station back in 1994 and 95. These missions provided invaluable insights into how the human body adapts and suffers during extended weightlessness. Scott Kelly's famous twin study, conducted with his brother Mark, who remained on Earth, revealed fascinating and concerning changes. Scott's telomeres, the protective caps on chromosomes, actually lengthened during spaceflight, though they shortened again upon return. His gut microbiome shifted, his gene expression changed, some cognitive functions slowed. Most changes reversed after returning to Earth, but not all. We are still learning what long-duration spaceflight does to human physiology. A Mars mission would push these boundaries even further. Astronauts would experience microgravity during both transit phases, potentially 18 months total, plus reduced gravity on Mars itself, which is only about 38% of Earth's. We simply do not know with certainty how human bodies will respond to years of reduced gravity followed by the sudden shock of Earth's full gravitational pull upon return. Some researchers propose artificial gravity as a solution. By spinning a spacecraft or a section of it, you can generate centrifugal force that mimics gravity. This concept has appeared in science fiction for decades. Think of the rotating station in 2001, A Space Odyssey. But implementing it in reality presents enormous engineering challenges. The spacecraft must be large enough that the rotation rate remains slow. Otherwise, the Coriolis effect creates disorienting sensations and nausea. Building such a massive rotating structure and launching it from Earth adds tremendous cost and complexity. Another approach involves intensive exercise regimens combined with pharmaceutical interventions. Current ISS astronauts exercise approximately 2 hours daily using specially designed resistance machines and treadmills with harness systems. This slows bone and muscle loss but does not eliminate it. Researchers are investigating drugs that might help maintain bone density and muscle mass, but we lack long-term data on their effectiveness during multi-year missions. Radiation remains perhaps the most stubborn challenge. Unlike microgravity effects, which can be partially mitigated through exercise, radiation damage accumulates invisibly. Every galactic cosmic ray that passes through your body deposits energy, potentially damaging DNA. Over a 3-year mission, astronauts would receive radiation doses far exceeding what is considered safe for terrestrial workers. Estimates suggest a Mars mission could increase lifetime cancer risk by several percentage points, a statistically significant elevation. Shielding helps but has limits. Water, polyethylene, and other hydrogen-rich materials absorb radiation effectively, but adding enough shielding to truly protect the crew increases mass dramatically. Every kilogram you add to the spacecraft requires more fuel to accelerate and decelerate, which requires more fuel to carry the fuel in an exponential spiral that quickly becomes unmanageable. Engineers must strike a delicate balance between protection and practicality. Solar particle events, bursts of radiation from solar flares and coronal mass ejections, pose acute dangers. During such events, astronauts would need to shelter in heavily shielded compartments for hours or even days. The spacecraft must carry sensors to detect incoming radiation and provide early warning. Ideally, mission planners would schedule launches during periods of lower solar activity, though the Sun does not always cooperate with human timetables. Some visionary concepts propose electromagnetic shielding, generating a magnetic field around the spacecraft to deflect charged particles, similar to how Earth's magnetosphere protects us. This remains largely theoretical, requiring superconducting magnets and enormous power supplies. Perhaps future generations will develop such technology, but it lies beyond our immediate capabilities. So here we stand at the edge of possibility. We know how long the journey takes, approximately 3 years round trip. We understand the physiological and psychological challenges awaiting those brave enough to go. We have identified the technologies needed and begun developing them. But the gap between knowing and doing remains vast. The question is not merely whether we can reach Mars. We almost certainly can, with sufficient resources and political will. The question is whether we can do so while keeping our astronauts alive and healthy enough to return. And that question does not yet have a definitive answer. Let us pause for a moment and zoom out. We have been discussing timelines and trajectories, radiation and muscle loss, orbital windows and transfer orbits. But beneath all these technical details lies a more fundamental question. Why does it take so long? Why can we not simply build faster rockets and cut the journey from months to weeks? The answer lies in one of the most unforgiving equations in all of physics, the Tsiolkovsky rocket equation, named after the Russian scientist Konstantin Tsiolkovsky, who derived it in 1893. This equation describes the relationship between a rocket's velocity, the efficiency of its engine, and the amount of propellant it must carry, and it is brutally exponential. Here is the essence. To go faster, you need more fuel. But more fuel means more mass. And more mass requires even more fuel to accelerate. This creates a vicious cycle. If you want to double your speed, you do not merely double your fuel, you might need to quadruple it, or worse. The numbers spiral out of control with terrifying speed. Consider a simple example. Imagine you want to accelerate a 1,000-kilogram spacecraft to a certain velocity using a chemical rocket. You might need 3,000 kilograms of propellant. Now imagine you want to go twice as fast. You might need 15,000 kilograms of propellant, 5 times more, not 2 times. Want to go 3 times faster? Perhaps 80,000 kilograms. The exponential nature of the equation makes high-speed travel extraordinarily expensive in terms of mass. This is why the Hohmann transfer orbit remains the standard approach for interplanetary missions. Yes, it is slow. Yes, it takes 6 to 9 months. But it minimizes the fuel required, which means we can actually build rockets capable of making the journey. Faster trajectories exist. They are called fast conjunction or opposition class missions, but they demand so much additional propellant that they become impractical with current technology. The fundamental problem is energy. Moving through space requires energy, lots of it, and we must carry all that energy with us in the form of chemical propellants. Unlike an airplane, which draws oxygen from the atmosphere to burn its fuel, a rocket must carry both fuel and oxidizer. Unlike a car, which pushes against the road to accelerate, a rocket has nothing to push against except its own expelled exhaust. Every joule of kinetic energy the spacecraft gains must come from propellant carried from Earth. Chemical rockets, the kind we have used since the dawn of the space age, extract energy by combining fuel and oxidizer in violent combustion. Liquid hydrogen and liquid oxygen produce an extremely hot, fast-moving exhaust. Methane and oxygen offer a good balance of performance and practicality, but there are hard physical limits to how much energy chemical bonds can release. We have nearly optimized chemical rocket performance. The Saturn V's F1 engines from the 1960s remain among the most powerful ever built. Modern engines like SpaceX's Raptor are more efficient, but not dramatically so. We are approaching the ceiling of what chemistry can provide. This is why propulsion engineers dream of alternative approaches. Nuclear thermal propulsion, which we mentioned earlier, offers roughly double the efficiency of chemical rockets by using nuclear fission to heat hydrogen to extreme temperatures. Ion engines, which accelerate charged particles using electric fields, achieve even higher efficiencies but produce minuscule thrust, useful for robotic probes but insufficient for crewed missions requiring faster acceleration. Then there are more exotic concepts. Nuclear pulse propulsion, the idea of detonating small nuclear bombs behind the spacecraft to push it forward, was seriously studied in the 1950s and 60s under Project Orion. The physics actually works. Such a system could theoretically achieve velocities far beyond chemical rockets, potentially reducing Mars transit to weeks. But the political, environmental, and safety concerns of launching thousands of nuclear weapons into space have kept this concept firmly in the realm of speculation. Fusion propulsion represents perhaps the ultimate dream. If we could harness the same process that powers the Sun, fusing hydrogen atoms into helium and releasing tremendous energy, we could theoretically achieve extraordinary speeds. A fusion rocket might reach Mars in a month or less. But controlled fusion remains elusive even for terrestrial power generation, despite decades of research and billions of dollars invested. Achieving compact, lightweight fusion propulsion for spacecraft lies far in our future, if it proves possible at all. Some researchers propose even more radical ideas: solar sails that harness the pressure of sunlight itself, requiring no propellant at all. Laser-driven sails that could be pushed by powerful ground-based or orbital lasers, potentially accelerating small probes to a fraction of light speed. Antimatter engines that would annihilate matter and antimatter to release energy with perfect efficiency. These concepts range from technically plausible to wildly speculative, but none are ready for human Mars missions in the foreseeable future. So we return to chemical rockets with nuclear thermal as a promising near-term upgrade. And we accept that reaching Mars will take months, not days. We design our missions around this reality. We plan for long transits, extended surface stays, and long return journeys. We engineer systems to keep humans alive and healthy for 3 years in the most hostile environment our species has ever attempted to inhabit. But wait, there is another factor we have not yet discussed, one that could significantly complicate our carefully calculated timelines. Communication delays. When you are on Mars, you cannot simply call mission control in Houston and have a real-time conversation. Light itself, the fastest thing in the universe, takes time to cross the gulf between planets. At Mars' closest approach to Earth, a radio signal requires roughly 3 minutes to make the journey. At maximum separation, that delay stretches to over 22 minutes, one way. This means that if an astronaut on Mars encounters a critical problem and radios Earth for help, they must wait anywhere from 6 to 44 minutes for a response. In an emergency, that delay could prove fatal. Unlike the Apollo missions, where communication lag was merely a couple of seconds, Mars crews must be prepared to handle crises autonomously. They cannot rely on real-time guidance from experts back home. This communication constraint affects everything from daily operations to emergency protocols. Surgeries, if needed, must be performed by crew members, with mission control offering only delayed advice. Complex repairs must be troubleshot locally. Psychological support from family and counselors comes with an awkward, conversation-breaking lag. The crew must function as an independent unit, self-sufficient in ways no previous space mission has required. Training for such autonomy takes years. Mars astronauts must be cross-trained in medicine, engineering, geology, biology, and psychology. Each crew member needs redundant skills so that the loss of any individual does not cripple the mission. Selection processes must identify people who can maintain composure, creativity, and cooperation under sustained stress and isolation. These individuals will be among the most carefully chosen human beings in history. NASA and other space agencies have conducted analog missions on Earth to study how crews perform during long-duration isolation. The Mars Desert Research Station in Utah places volunteers in simulated Martian habitats for weeks at a time. The HIC's project in Hawaii isolated crews for up to a year in a dome on the slopes of Mauna Loa volcano. Russia's Mars 500 experiment confined 6 volunteers for 520 days, the approximate duration of a Mars mission, in a windowless facility in Moscow. These studies revealed critical insights. Crew cohesion tends to deteriorate over time without careful management. Sleep patterns shift, affecting cognitive performance. Monotony becomes a serious psychological threat. Conflicts that might seem trivial under normal circumstances can escalate dramatically in confined, inescapable environments. Successful crews develop strong communication practices, maintain meaningful routines, and find ways to preserve individual identity within the group dynamic. The psychological dimension of Mars travel deserves as much engineering attention as the propulsion systems or life support. A rocket that functions perfectly means nothing if the crew inside loses the mental resilience to operate it. We must design not just machines that can survive the journey, but social environments where humans can thrive, or at least endure. Some proposed mission architectures include virtual reality systems allowing astronauts to escape their confined quarters and experience simulated Earth environments. Others suggest carefully curated entertainment libraries, regular private communication sessions with family, and even onboard gardens that provide both fresh food and psychological comfort through nurturing living things. The color of interior lighting, the textures of surfaces, the sounds allowed to propagate through the habitat, every sensory detail matters when you cannot step outside for 3 years. We often imagine space exploration as a purely technical challenge, building better rockets, designing more efficient engines, calculating more precise trajectories. But it is equally a human challenge. The spacecraft is merely the container. The precious cargo is consciousness itself. Fragile minds and bodies evolved over millions of years for African savannas, now asked to survive the void between worlds. And perhaps this is the most profound aspect of the Mars journey. It is not merely a test of our engineering prowess, it is a test of our humanity. Can we maintain our sanity, our compassion, our curiosity, our will to survive when separated from everything that made us? Can we carry Earth within us when Earth itself becomes just another star in the sky? The astronauts who eventually make this journey will not merely be explorers, they will be philosophers conducting an experiment in the most fundamental questions of human existence. What does it mean to be human when you can no longer see your home? What does it mean to be alive when death surrounds you in every direction? What does it mean to hope when rescue lies impossibly far away? These are not questions that appear in engineering textbooks, but they may determine whether Mars missions succeed or fail more than any propulsion system ever could. We have explored the physics, the biology, and the psychology of reaching Mars. Now let us examine the actual mission architectures that space agencies and private companies are developing. These are not science fiction fantasies, they are detailed engineering plans backed by billions of dollars and decades of research. NASA's current approach centers on a concept called the Moon to Mars initiative. The idea is to use the Moon as a proving ground, testing technologies and operational procedures in an environment that is merely 3 days from Earth before committing to the much riskier Mars journey. The Artemis program aims to return humans to the lunar surface, establish a sustained presence there, and gradually build the capabilities needed for deep space exploration. A crucial element of this strategy is Gateway, a small space station planned to orbit the Moon. Unlike the International Space Station, which circles Earth every 90 minutes, Gateway will occupy a highly elliptical orbit that carries it far from the Moon and back again. This orbit requires minimal fuel to maintain and provides an excellent staging point for missions deeper into the solar system. Astronauts could assemble Mars-bound spacecraft at Gateway, transfer supplies and crew, and depart from a location already beyond Earth's gravitational well. The deep space transport, sometimes called the Mars Transit Vehicle, represents NASA's conceptual spacecraft for the actual journey. Designs envision a large habitat module where 4 to 6 astronauts would live during the months-long transit, connected to propulsion systems capable of the necessary velocity changes. Solar electric propulsion, using ion engines powered by large solar arrays, could provide efficient thrust for portions of the journey, with chemical rockets handling the high-thrust maneuvers at departure and arrival. NASA's timeline has shifted repeatedly over the years, buffeted by changing budgets and political priorities. Current projections suggest a crewed Mars orbital mission where astronauts fly to Mars, orbit the planet without landing, and return could occur sometime in the late 2030s or early 2040s. An actual surface landing would follow later, perhaps in the mid-2040s. These dates remain aspirational. Every change in presidential administration brings potential shifts in space policy. SpaceX, under Elon Musk's leadership, has pursued a dramatically different approach, one characterized by speed, iteration, and calculated risk-taking. The Starship vehicle represents the centerpiece of this strategy. Standing roughly 120 meters tall when mounted atop its super-heavy booster, Starship would be the largest and most powerful rocket ever flown. Its fully reusable design aims to slash launch costs by orders of magnitude, fundamentally changing the economics of space travel. Musk's stated goal is to make humanity a multi-planetary species, with Mars as the first step. His proposed architecture involves launching multiple starships, some carrying crew, others carrying cargo and propellant. Orbital refueling would allow the crewed vehicle to depart Earth with full tanks, enabling faster trajectories than the minimum energy Hohmann transfer. SpaceX has suggested that optimized trajectories could reduce transit time to as little as 3 to 4 months, though independent analyses suggest 6 months remains more realistic with near-term technology. The SpaceX approach embraces a concept called Design for Mars. Rather than developing separate vehicles for lunar and Martian missions, Starship is intended from the beginning to land on Mars, using its stainless steel construction to withstand the thermal stresses of atmospheric entry. The vehicle would land vertically on its own engines, similar to how Falcon 9 boosters return to Earth today, but on a far grander scale. One critical innovation in SpaceX's plan involves manufacturing propellant on Mars for the return journey. Starship would land with empty or nearly empty tanks, unable to return home without refueling. Using the Sabatier reaction, combining Martian atmospheric carbon dioxide with hydrogen to produce methane and water, robotic systems would generate propellant over the 18-month surface stay. The methane would fuel the engines, while oxygen extracted from carbon dioxide would serve as the oxidizer. This in-situ resource utilization eliminates the need to carry return propellant all the way from Earth, dramatically reducing mission mass and cost. As we discussed earlier, the MOXIE experiment aboard Perseverance demonstrated oxygen extraction from the Martian atmosphere works in practice. Scaling this to produce the dozens of metric tons needed for a crewed return represents a significant engineering challenge, but the fundamental chemistry is sound. China has emerged as an increasingly ambitious player in Mars exploration. The Tianwen-1 mission, which arrived at Mars in May of 2021, successfully placed both an orbiter and a rover named Zhurong on the Martian surface. This made China only the second nation to operate a rover on Mars after the United States. Chinese space officials have announced intentions to conduct a Mars sample return mission before the end of this decade and have discussed crewed Mars missions as a long-term goal, potentially in the 2040s. The China National Space Administration has provided fewer details about their crewed Mars architecture compared to NASA or SpaceX, but their track record of meeting ambitious deadlines, including constructing their own space station, Tiangong, and conducting increasingly complex lunar missions, suggests they should be taken seriously. The geopolitical dimension of space exploration cannot be ignored. Competition between nations has historically accelerated technological development, as the original space race between the United States and Soviet Union demonstrated. The European Space Agency, while lacking the budget for independent crewed Mars missions, contributes critical technologies and expertise. ESA has partnered with NASA on numerous Mars missions and would likely participate in any international crewed effort. Their ExoMars program, though delayed by geopolitical complications, aimed to search for signs of past life on Mars using a sophisticated rover named Rosalind Franklin. Private companies beyond SpaceX are also entering the arena. Blue Origin, founded by Amazon's Jeff Bezos, focuses primarily on lunar infrastructure, but has expressed long-term interest in Mars. Rocket Lab, Relativity Space, and other emerging launch providers are developing vehicles that could support Mars missions with cargo and supplies, even if they lack the capacity for crewed flights. Perhaps the most intriguing proposals come from those advocating for a one-way journey. Mars One, a now-defunct Dutch organization, generated enormous publicity and considerable controversy by proposing to send volunteers to Mars with no plan for return. The idea was to establish a permanent colony from the very beginning, with settlers accepting that they would live and die on Mars. While Mars One collapsed due to funding and credibility issues, the underlying concept sparked serious discussion. Some argue that eliminating the return journey simplifies mission architecture enormously. You no longer need to carry or manufacture return propellant. You no longer need an ascent vehicle capable of escaping Martian gravity. The mass savings could be redirected toward more robust habitats, more supplies, more redundancy. Colonists could focus entirely on building a sustainable settlement rather than preparing for departure. Others find this approach ethically troubling. Can anyone truly give informed consent to permanent exile from Earth? What happens when colonists develop medical conditions requiring treatments unavailable on Mars? What about psychological breakdowns, interpersonal conflicts that cannot be resolved, or simply the crushing weight of homesickness that never fades? Without the option of return, Mars becomes not an adventure, but a prison, however beautiful its rust-colored sunsets might be. The ethical dimensions of Mars colonization extend further. Who decides who goes? If tickets become available for purchase, does Mars become a refuge only for the wealthy? If governments select astronauts, what criteria apply? Should we prioritize scientific expertise, physical fitness, psychological resilience, genetic diversity for establishing a new population, or some combination of all these factors? What rights would Martian colonists possess? Would they remain citizens of their Earth nations or form their own governance? If valuable resources are discovered, rare minerals, unique scientific specimens, perhaps even evidence of life, who owns them? Existing space treaties drafted during the 1960s, when Mars colonization seemed impossibly distant, provide limited guidance. And then there is the question of contamination, both forward and backward. Forward contamination refers to the possibility that Earth microbes carried by spacecraft could survive on Mars, potentially interfering with any native Martian life or confusing our search for it. Backward contamination represents the terrifying scenario where Martian organisms, if they exist, are brought to Earth with unknown consequences for our biosphere. Planetary protection protocols require spacecraft to be meticulously sterilized before launch, but perfect sterilization is nearly impossible. Human beings, in particular, carry trillions of microorganisms in and on their bodies. A crewed Mars mission would inevitably introduce Earth life to Mars. Some argue this makes protecting Mars from contamination hopeless, and we should abandon the pretense. Others insist we must delay crewed missions until we have thoroughly searched for Martian life robotically. These debates may seem abstract compared to the engineering challenges of propulsion and life support, but they will shape the missions that eventually fly. Space agencies operate within political contexts that respond to public values. The ethical frameworks we develop now will determine whether Mars exploration proceeds wisely or recklessly, inclusively or exclusively, with humility or hubris. For now, the most realistic, near-term pathway to crewed Mars missions combines elements from multiple approaches. NASA's steady, methodical development of deep space capabilities through Artemis and Gateway, SpaceX's rapid iteration and cost reduction through Starship, international partnerships that share financial burdens and distribute expertise, private sector innovation that challenges government bureaucracies to move faster, public engagement that maintains political support across the decades required to see these visions through. The journey to Mars will not result from a single heroic effort like Apollo. It will emerge from sustained commitment across generations, engineers who design systems they will not live to see fly, taxpayers who fund programs whose benefits accrue to their grandchildren, astronauts who accept risks for discoveries that may not be fully understood for centuries. Let us now consider something we have touched upon but not fully explored: the return journey. We have spent considerable time discussing the outbound trip and the surface stay, but the voyage home presents its own unique challenges. In many ways, coming back is harder than going. When astronauts depart Mars for Earth, they face a cruel irony. They have just spent 18 months on a planet with only 38% of Earth's gravity. Their bodies have partially adapted to this reduced load. Muscles have weakened despite rigorous exercise. Bones have lost density. Cardiovascular systems have recalibrated, and now they must endure another 6 to 9 months of near-zero gravity during the transit home, followed by the brutal shock of Earth's full gravitational pull upon arrival. Think about what this means. An astronaut leaves Earth at peak physical condition. These are among the fittest, most carefully screened humans alive. They spend up to 9 months in microgravity traveling to Mars, losing strength and bone mass despite countermeasures. They spend 18 months on Mars at reduced gravity, partially recovering, but never fully returning to Earth normal conditioning. Then they spend another 6 to 9 months in microgravity returning home. By the time they reach Earth, they will have spent nearly 2 years in conditions that actively degrade the human body. Current International Space Station astronauts require extensive rehabilitation after missions of 6 months to a year. They often cannot walk unassisted immediately after landing. Their balance is impaired. Their muscles tremble under Earth's gravity. Recovery takes weeks or months. Now imagine astronauts returning from Mars after 3 years. We genuinely do not know how their bodies will respond. We are venturing into uncharted physiological territory. Some researchers worry about permanent damage. Studies on ISS astronauts have documented changes to brain structure, fluid shifts that alter the shape of the brain within the skull. Vision problems have affected a significant percentage of long-duration astronauts, a condition called spaceflight-associated neuroocular syndrome. Some of these effects persist long after return to Earth. A 3-year mission could potentially cause irreversible harm. This uncertainty has led some to propose that Mars astronauts should remain on Mars permanently, not as punishment, but as medical prudence. If the return journey and Earth reintegration pose serious health risks, perhaps the kindest option is to let settlers adapt fully to Martian gravity and build lives there. This transforms Mars missions from expeditions into emigrations, from temporary visits into permanent relocations. But let us assume our astronauts do attempt the return. They have survived the surface stay, manufactured their propellant, loaded their ascent vehicle, and launched from Mars. They have rendezvoused with their transit vehicle in Mars orbit, or perhaps their Starship is capable of the entire round trip, depending on the architecture. Now they face the long coast home. The psychological challenges of the return may actually exceed those of the outbound journey. On the way to Mars, astronauts are sustained by anticipation, the thrill of approaching an alien world, the excitement of upcoming exploration, the sense of venturing into history. On the way home, that excitement has faded. They have seen what they came to see. Now they must simply endure months of confinement before reaching a destination they have already known their entire lives. This phenomenon has been observed in Antarctic expeditions, submarine deployments, and other isolated missions. The return portion often proves psychologically harder than the outbound. Motivation wanes. Interpersonal tensions that were suppressed by shared purpose resurface. Depression and anxiety become more prevalent. The term third quarter phenomenon describes this dip in morale that typically occurs about 3/4 through an isolated mission. Mission planners must account for this. Perhaps the return journey should include different activities, new experiments, or structured goals to maintain engagement. Perhaps communication with Earth, now increasingly possible as the distance shrinks, can provide fresh stimulation. Perhaps pharmaceutical interventions can help stabilize mood during this vulnerable period. These are not trivial concerns. A crew that loses psychological cohesion during the return could make fatal errors in the final critical phases. And those final phases are indeed critical. Returning from Mars requires precise navigation and timing. The spacecraft must enter Earth's atmosphere at exactly the right angle, too steep, and friction generates heat exceeding the vehicle's thermal protection. The spacecraft burns up. Too shallow, and the vehicle skips off the atmosphere like a stone off water, careening back into space with insufficient fuel to attempt another entry. The entry corridor for a Mars return is narrower than for lunar returns because the spacecraft approaches at higher velocity. Returning from the Moon, Apollo capsules entered at approximately 11 kilometers per second. Returning from Mars, vehicles will enter at roughly 12 to 14 kilometers per second, significantly faster. This higher speed generates more heat and leaves less room for error. Modern thermal protection systems can handle these conditions, but the margins are thin. The heat shield must be in perfect condition after 3 years in space, no micrometeorite damage, no degradation from radiation or thermal cycling. Inspection and repair capabilities must exist, or complete confidence in the shield's durability must be established before departure from Mars. The entry, descent, and landing sequence for returning astronauts will likely involve a combination of aerodynamic braking, using atmospheric friction to slow down, and parachutes or retropropulsion for the final descent. SpaceX favors propulsive landing, where engines fire to bring the vehicle to a gentle touchdown. Traditional capsule designs use parachutes to descend into the ocean. Each approach has advantages and risks. Once the astronauts are safely on Earth's surface, the mission is technically complete. But in another sense, it has just entered a new phase, the phase of understanding what was accomplished. The scientific samples collected on Mars must be analyzed. The geological, atmospheric, and biological data must be interpreted. The engineering lessons must be incorporated into future mission designs. The human experiences must be documented and studied. Mars sample return, bringing pieces of the red planet back to Earth laboratories, represents one of the highest scientific priorities. Robotic missions can conduct basic analyses on site, but the most sophisticated investigations require instruments too massive and power-hungry for spacecraft. A crewed mission could collect and curate samples with human judgment, selecting the most scientifically valuable specimens and preserving them appropriately for the journey home. These samples could answer some of the most profound questions in science. Did life ever exist on Mars? If so, did it share a common origin with Earth life, perhaps transferred between planets aboard meteorites? Or did it arise independently, representing a second genesis? Finding even fossil microbes on Mars would revolutionize biology, demonstrating that life emerges readily given the right conditions. Finding living organisms would be among the most significant discoveries in human history. But handling Martian samples on Earth requires extraordinary precautions. Until we confirm that Mars harbors no organisms harmful to terrestrial life, samples must be contained within facilities rivaling the highest biosafety laboratories. The potential for contamination in either direction demands protocols we have never before implemented. Some scientists argue samples should first be studied in orbital facilities far from Earth's biosphere until safety is established. The returning astronauts themselves would require quarantine. Apollo astronauts were isolated for 3 weeks after returning from the Moon until scientists confirmed lunar material posed no biological threat. Mars astronauts might face longer and more rigorous isolation. Medical examinations would assess the effects of long-duration spaceflight. Psychological evaluations would explore the mental impacts of the experience. Debriefings would extract operational lessons for future missions. And then eventually the astronauts would rejoin society. They would become celebrities, certainly the most famous explorers since Armstrong and Aldrin, perhaps the most famous in history. They would spend years giving interviews, writing memoirs, advising future missions, inspiring the next generation. Their experience would become part of humanity's collective story, retold countless times, mythologized and analyzed in equal measure. But they would also be forever changed. No one who travels to another world returns the same person. The overview effect, that profound shift in perspective reported by astronauts who see Earth from space, would be amplified beyond anything previously experienced. These individuals would have seen Earth as a pale blue dot, a fragile mote suspended in an infinite void. They would have stood on alien soil, breathed recycled air, watched unfamiliar stars wheel overhead. They would have confronted their mortality in ways few humans ever have. Some might struggle to readjust. The intensity of the Mars experience could make ordinary life feel hollow. Relationships formed before the mission might strain under the weight of transformation. The psychological literature on returning explorers, soldiers, and others who have endured extraordinary experiences suggests that reintegration is rarely seamless. Support systems must be in place, not just for the mission, but for lifetimes afterward. Others might find the experience transcendent, a source of purpose and meaning that enriches everything that follows. They might become teachers, leaders, advocates for further exploration. They might channel their unique perspective into art, philosophy, or science. They might help humanity understand its place in the cosmos in ways that shift our collective consciousness. This is the full arc of a Mars mission, not merely the technical trajectory of a spacecraft, but the human journey of transformation. From launch to landing, from exploration to return, from quarantine to reintegration, the mission spans years and reshapes lives. It is an odyssey in the original sense, a voyage of discovery that tests the voyagers and returns them fundamentally altered. Now let us step back and place this entire endeavor in cosmic perspective. We have been discussing months and years, 6 months to arrive, 18 months on the surface, 9 months to return. These timescales feel enormous to us, accustomed as we are to overnight flights and instant communication. But in the context of the universe, they are less than the blink of an eye. Light from the Sun takes approximately 8 minutes to reach Earth. Light from the nearest star beyond our Sun, Proxima Centauri, takes over 4 years. Light from the center of our own Milky Way galaxy takes roughly 26,000 years to reach us. Light from the Andromeda Galaxy, our nearest large galactic neighbor, has been traveling for over 2 million years before it enters our telescopes, and the observable universe extends nearly 14 billion light-years in every direction. Against this backdrop, the few months required to reach Mars seem almost trivial. We are talking about crossing a gap of 55 to 400 million kilometers, Distances that sound impressive until you realize the Milky Way itself spans 100,000 light-years, or roughly 950 quadrillion kilometers. Mars is right next door. It is practically in our living room. The challenge is not the distance itself, but our current inability to traverse even modest cosmic distances at reasonable speeds. This perspective should inspire both humility and determination. Humility because it reveals how small we are, how limited our current capabilities, how vast the universe we aspire to explore. But also determination because it shows us that Mars is merely the first step on an infinite staircase. If we can reach Mars, truly establish a sustained human presence there, we prove something profound about our species. We prove that we are not bound to a single world, that we can adapt and survive beyond our birthplace, that the universe might someday be our home. Every long journey begins with a single step, as the ancient proverb notes. For humanity, Mars represents that step. Not the destination, but the beginning. Not the goal, but the proof of concept. If we can thrive on Mars, perhaps we can reach the moons of Jupiter and Saturn. If we can reach those moons, perhaps we can someday build generation ships that crawl toward other stars over centuries. If we can do that, perhaps our descendants will spread across the galaxy over millions of years, filling countless worlds with a legacy of life that began on a small blue planet orbiting an ordinary yellow star. This is the grand context in which we must understand Mars' travel times. Yes, 3 years is long. Yes, the journey is dangerous. Yes, the challenges are immense. But we are not merely trying to plant flags or collect rocks. We are attempting to extend the reach of consciousness itself, to ensure that the universe has witnesses who can appreciate its beauty, to spread the light of awareness into the cosmic darkness. Some philosophers argue that this is humanity's ultimate purpose, if purpose is even a meaningful concept in a universe governed by physical law. We are the cosmos becoming aware of itself, as Carl Sagan famously observed. We are matter that has learned to contemplate matter. We are stardust that has arranged itself into configurations capable of wondering about stars. And now that wandering stardust is preparing to voyage to another dusty world, continuing a journey that began when the first replicating molecules emerged in Earth's primordial oceans nearly 4 billion years ago. When we discuss the challenges of Mars travel, the radiation, the isolation, the physiological degradation, we are really discussing the growing pains of a species reaching toward maturity. Every transition involves difficulty. Every expansion of capability requires sacrifice. The first fish that flopped onto land faced challenges far exceeding anything those fish had evolved to handle. The first primates that descended from trees and walked upright exposed themselves to predators and hardships. The first humans that left Africa and spread across the globe confronted climates and environments utterly foreign to their ancestors. Each of these transitions seemed impossible from the perspective of those who had not yet made them. And each was accomplished not by a single heroic individual, but by countless generations, incrementally pushing boundaries, failing and learning, adapting and advancing. Mars will be the same. The first missions will be tentative, limited, fraught with danger. Later missions will benefit from lessons learned. Eventually, perhaps within a few generations, travel to Mars might become routine, even mundane. Imagine telling a medieval peasant that their descendants would routinely hurtle through the sky at 900 kilometers per hour inside metal tubes, eating snacks and watching entertainment, crossing oceans in hours rather than months. They would not believe you. They could not conceive of such a world. And yet here we are, barely noticing the miracle of flight because it has become ordinary. Someday, Mars travel might be equally ordinary. Spaceflight attendants might welcome passengers aboard interplanetary vessels. Children might grow up on Mars, never having experienced Earth's crushing gravity, never having seen an ocean or a forest except in videos. Martian cities might develop their own cultures, their own traditions, their own identities distinct from any Earth nation. A new branch of humanity might emerge, adapted to Mars, shaped by Mars, belonging to Mars in ways we cannot fully anticipate. This future is not guaranteed. It depends on choices we make now, investments in technology, commitments to exploration, willingness to accept risk and delay gratification for rewards that may not materialize for decades. It depends on cooperation across national boundaries and collaboration across generations. It depends on maintaining hope and ambition even when progress seems slow or setbacks occur. But if we do make those choices, if we do sustain that commitment, then the timescales we have discussed, the months of travel, the years of mission duration, will eventually shrink. As technology advances, as infrastructure develops, as experience accumulates, journeys that now require years might someday require only weeks or days. The first transatlantic flight took over 33 hours. Today, supersonic concepts promise to cut that to under 2 hours. The first Mars missions will take 3 years. Future missions, powered by technologies we cannot yet fully envision, might take far less. Nuclear thermal propulsion could cut transit time significantly, as we discussed. Nuclear electric systems combining nuclear power with highly efficient ion engines could reduce them further. Fusion propulsion, if achieved, might reduce them further still. And technologies we have not yet imagined, perhaps exploiting physics we do not yet understand, might someday make even the vast distances between stars tractable. This is not wishful thinking. This is the pattern of human history. We consistently underestimate how much technology will advance over long timescales, while overestimating how quickly particular breakthroughs will occur. A Mars mission in the 2040s might use technologies only marginally better than what we have today. But a Mars mission in the 2140s, a century hence, might use technologies that seem like magic to our current understanding. Consider how much change between 1903, when the Wright brothers first flew at Kitty Hawk, and 2003, a century later. In 1903, a 12-second flight covering 36 meters represented the bleeding edge of human capability. In 2003, the International Space Station orbited Earth continuously, inhabited by rotating crews who conducted scientific research in microgravity. A century transformed flight from a barely achievable novelty into a mature technology supporting global civilization. What might the next century bring for spaceflight? If progress continues and there is no physical law preventing it, Mars might become a thriving colony, the outer planets might be explored, and the first tentative probes might be departing toward nearby stars. Our great-great-grandchildren might look back at our era the way we look back at the Wright brothers, with appreciation for the pioneers who took the first difficult steps, but also with amusement at how limited those early efforts were. This long view does not diminish the achievements of our era. The Wright brothers did not fail simply because modern aircraft are better. They succeeded magnificently, opening a door that others would walk through. Similarly, the first Mars explorers will succeed magnificently, even if their technology seems primitive to future generations. They will be the ones who proved it could be done, who took the risks and made the sacrifices, who transformed Mars from a destination into a home. And that transformation from destination to home is perhaps the most significant shift of all. When we discuss travel times to Mars, we implicitly assume Earth remains home and Mars is somewhere we visit. But if Mars becomes a permanent settlement, that assumption changes. For Martians, travel times work in reverse. Their home is Mars. Earth becomes the distant destination requiring months to reach. Future Martians might feel about Earth the way descendants of immigrants feel about ancestral homelands, connected by history and heritage, but separated by distance and divergent experience. They might travel to Earth as tourists, as pilgrims, as curious visitors seeking to understand where their species originated. Or they might never visit at all, content with their Martian lives as connected to Earth as we are to the African savanna where our species evolved. This bifurcation of humanity into Terrans and Martians, perhaps eventually into dozens of branches spread across the solar system and beyond, raises profound questions. Will we remain one species? Will Martian conditions and Martian selection pressures gradually shape different traits? Over thousands or millions of years, might Martians evolve into something new, something adapted to their world in ways that make them distinct from their Earth-bound cousins? Such speculations extend far beyond our current discussion of travel times, but they are implicit in that discussion. When we ask how long it takes to reach Mars, we are really asking how long it takes to extend humanity's reach. And once that reach extends, it develops its own momentum, its own logic, its own trajectory into futures we can barely imagine. Let us return from those cosmic vistas to the concrete realities facing mission planners today. We have discussed idealized trajectories and theoretical timelines, but actual missions must contend with countless practical complications. The gap between textbook physics and operational spaceflight is vast, filled with engineering constraints, budget limitations, and the stubborn unpredictability of complex systems. Consider the problem of launch windows. We mentioned that favorable alignments between Earth and Mars occur every 26 months, but favorable does not mean identical. Some windows are better than others. The eccentricity of Mars' orbit, its deviation from a perfect circle, means that some oppositions bring Mars much closer than others. The famous opposition of August 2003 brought Mars within 56 million kilometers of Earth, the closest approach in nearly 60,000 years. The opposition of October 2020 saw Mars at a more typical distance of approximately 62 million kilometers. These variations matter. A closer approach means shorter travel times and lower fuel requirements, or alternatively, the ability to carry more payload for the same fuel expenditure. Mission planners scrutinize upcoming windows years in advance, calculating optimal departure dates, arrival dates, and trajectory parameters. A mission that launches at the wrong moment within a window might add weeks to its transit time compared to one that launches at the optimal instant. Weather on Earth also affects launches. Rockets cannot fly through thunderstorms or excessively high winds. A single day's delay due to weather might not matter much for a flight to the International Space Station, but for a Mars mission with a narrow launch window, delays can cascade into serious problems. If weather forces too many postponements, the window might close entirely, requiring a 26-month wait for the next opportunity. Then there are the spacecraft systems themselves. Rockets are extraordinarily complex machines with millions of components that must function correctly. A sensor malfunction, a valve that sticks, a software glitch, any of countless issues can scrub a launch. The history of spaceflight is littered with missions delayed by technical problems, sometimes by days, sometimes by months, occasionally by years. The Curiosity rover, which landed on Mars in August of 2012, was originally planned for launch in 2009. Technical challenges with its heat shield and other systems forced a delay to the 2011 window. Such delays are frustrating but often necessary. Launching before a spacecraft is truly ready invites disaster. The loss of the Mars Climate Orbiter in 1999, caused by a simple confusion between metric and imperial units in the navigation software, demonstrates how small errors can destroy entire missions. For crewed missions, the stakes are infinitely higher. Robotic probes can be rebuilt if they fail. Human lives cannot be replaced. The pressure to ensure absolute reliability before committing astronauts to a 3-year journey will be immense. Some argue this pressure could delay crewed Mars missions indefinitely, as engineers always find one more issue to address, one more system to test, one more contingency to prepare for. This tension between boldness and caution defines human spaceflight. Too much caution and we never go anywhere. Too much boldness and we kill astronauts and destroy public support for exploration. Finding the right balance requires wisdom, experience, and a clear-eyed assessment of acceptable risk. Different cultures and organizations strike this balance differently. NASA, scarred by the Challenger and Columbia disasters, tends toward extreme caution. SpaceX, with its fail fast, learn fast philosophy, accepts higher risk in pursuit of rapid progress. The question of acceptable risk becomes particularly acute for Mars missions because rescue is impossible. When Apollo 13 suffered an oxygen tank explosion halfway to the Moon, Mission Control worked frantically to bring the crew home, improvising solutions with available materials. The astronauts barely survived, but they did survive, in part because the Moon is only 3 days away. A similar emergency on a Mars transit would unfold over months, with no possibility of rapid return and extremely limited options for improvisation. Some have proposed abort scenarios for Mars missions, trajectories that would allow a damaged spacecraft to swing around Mars and return to Earth without landing. These free return trajectories add constraints to mission design and may not always be feasible depending on the specific alignment of planets. Even when possible, they condemn the crew to many additional months in a potentially compromised vehicle. An abort is survival, not rescue. This reality shapes every aspect of Mars mission design. Redundancy becomes paramount. Critical systems must have backups, and those backups must have backups. The spacecraft must carry spare parts, repair tools, and crew members trained to fix virtually anything that might break. Medical capabilities must extend far beyond typical spaceflight provisions: surgery, dentistry, psychiatric care, treatment for radiation exposure, management of chronic conditions that might develop over 3 years. The mass implications of all this redundancy are staggering. Every kilogram of backup equipment, every spare component, every medical supply must be launched from Earth at enormous expense. Engineers must constantly weigh the probability of various failures against the mass cost of preparing for them. Some risks must simply be accepted because mitigating them would make the mission impossibly heavy. Food represents another massive challenge. Astronauts on the International Space Station receive regular resupply missions carrying fresh food. Mars astronauts must carry everything they will eat for 3 years, or grow it themselves. 3 years of food for a crew of 4 to 6 people amounts to thousands of kilograms, even with the most efficient freeze-dried and preserved provisions. Growing food on Mars or during transit could reduce this burden while providing psychological benefits: the comfort of fresh vegetables, the satisfaction of nurturing living things. Experiments on the ISS have successfully grown lettuce, radishes, and other crops in microgravity. Expanding this to meaningful food production requires larger growing facilities, reliable lighting, careful water and nutrient management, and protection from the radiation that would otherwise damage plants just as it damages humans. Some mission concepts propose sending cargo missions ahead of the crew, landing habitats, supplies, vehicles, and propellant production equipment on Mars before any humans arrive. This approach, sometimes called pre-positioning, reduces the mass that must travel with the crew and provides confirmation that critical systems are functioning before anyone commits to the journey. If a cargo landing fails, another can be attempted at the next window. If a crewed landing fails, people die. NASA's Mars Design Reference Architecture, a detailed study of potential mission approaches, envisions multiple cargo missions preceding the crew by 1 or 2 launch windows. By the time astronauts arrive, their habitat awaits them, fully deployed and tested. Their ascent vehicle sits fueled and ready. Supplies sufficient for the entire surface stay have been confirmed intact. This dramatically reduces risk compared to arriving with everything aboard a single spacecraft. SpaceX's approach differs, relying on the massive payload capacity of Starship to deliver everything needed in fewer launches. The sheer size of Starship, capable of carrying over 100 metric tons to Mars in some configurations, changes the calculus of mission planning. Rather than carefully minimizing mass, engineers can afford some inefficiency in exchange for speed and simplicity. Whether this approach will prove superior to the more methodical NASA strategy remains to be seen. The choice of landing site also affects mission timelines and complexity. Mars offers diverse terrain, ancient river valleys, towering volcanoes, deep canyons, polar ice caps, and vast plains. Scientifically interesting sites often present landing challenges. Jezero Crater, where Perseverance landed, was chosen because it contains an ancient river delta likely to preserve biosignatures, but its rocky terrain made landing hazardous. For crewed missions, safety considerations may override scientific preferences. Flat, boulder-free plains at low elevations offer the easiest landings and the densest atmosphere for aerobraking, but such sites may be scientifically mundane. The tension between where we want to go and where we can safely go will shape landing site selection for early missions. Water ice accessibility represents another critical factor. Sites near confirmed ice deposits enable easier extraction of water for drinking, agriculture, and propellant production. The mid-latitudes of Mars appear to harbor substantial subsurface ice, detectable by orbital radar. Landing near these deposits could dramatically simplify surface operations, but ice-rich regions may also present challenges, ground stability issues, extreme cold, or terrain complications. The Martian atmosphere, though thin, still matters for landing. Entry vehicles rely on atmospheric friction to shed most of their velocity. The denser the atmosphere, the more effective this braking. Mars' atmosphere is only about 1% as dense as Earth's at sea level, which limits its braking capacity. Landing at lower elevations, where the atmosphere is slightly denser, provides modest advantages. The massive Hellas Basin, the deepest impact crater on Mars, offers the densest atmosphere anywhere on the planet, but presents its own challenges. Dust storms add another variable. Martian dust storms can grow to encompass the entire planet, reducing sunlight by 90% or more and depositing fine particles on every exposed surface. The Opportunity rover, which operated for nearly 15 years, was ultimately killed by a global dust storm in 2018 that blocked sunlight from its solar panels. Crewed missions must either use nuclear power, immune to dust coverage, or design solar systems that can survive extended storms. The timing of arrival relative to dust storm season affects mission planning. Dust storms occur most frequently during southern hemisphere spring and summer, when Mars is closest to the Sun and surface heating is strongest. Landing during the calmer seasons reduces risk but constrains launch windows further. All of these factors, orbital mechanics, spacecraft readiness, landing site selection, atmospheric conditions, dust storms, and countless others, interact in complex ways. Mission planners use sophisticated computer models to simulate thousands of scenarios, optimizing trajectories and timelines while accounting for uncertainties. The 3-year mission duration we have discussed represents an idealized case. Actual missions may prove longer or shorter depending on circumstances. We have explored the technical and logistical dimensions of Mars travel extensively. Now let us turn to something equally important but often overlooked, the cultural and philosophical implications of this journey. How will reaching Mars change us as a species? What will it mean for our understanding of ourselves and our place in existence? Throughout human history, exploration has transformed not just maps, but minds. When European sailors first crossed the Atlantic, they did not merely discover new lands, they shattered a worldview. The existence of the Americas, unknown to classical authorities, demonstrated that ancient wisdom was incomplete. Indigenous peoples with entirely different cultures, technologies, and belief systems challenged assumptions about human nature and society. The encounter between worlds reshaped philosophy, religion, economics, and politics for centuries. The Copernican revolution, the realization that Earth orbits the Sun rather than vice versa, inflicted a similar wound on human pride. We were not the center of creation. Our planet was merely one world among several, circling an ordinary star. Later discoveries pushed us further from centrality. Our Sun occupies no special position in the Milky Way. Our galaxy is one among hundreds of billions. The universe has no center at all, or rather, every point is equally central and equally peripheral. Mars exploration continues this trajectory of cosmic humbling. When we set foot on another world, when we build shelters, grow crops, raise children on alien soil, we demonstrate definitively that Earth is not uniquely suited for life. We prove that consciousness can exist elsewhere, can thrive elsewhere, can call elsewhere home. This may seem obvious intellectually, but experiencing it viscerally will transform human self-understanding in ways we cannot fully predict. Consider the religious implications. Many faith traditions place Earth and humanity at the center of divine concern. The Earth was created for us. The stars were placed in the sky for our benefit. God's attention focuses here, on this world, on these creatures. How do such beliefs adapt when humanity spreads to other worlds? Does divine concern follow us to Mars? Do Martian-born children inherit the same spiritual status as Earth-born ones? These questions may seem abstract now, but they will become urgently concrete for believers who find themselves starting families on another planet. Some theologians have already begun grappling with these issues. The Vatican Observatory, one of the oldest astronomical research institutions in the world, employs Jesuit scientists who contemplate the theological implications of extraterrestrial life and human expansion into space. They generally conclude that faith can adapt, that the vastness of creation magnifies rather than diminishes divine glory. But not all believers will reach the same conclusions. The cultural negotiations around Mars settlement may prove as contentious as any engineering challenge. Secular philosophies face their own reckonings. Environmentalism, for instance, often emphasizes humanity's connection to Earth's biosphere, our embeddedness in natural systems, our responsibility to preserve the only home we have ever known. How does this framework adapt when we have two homes? Does Mars deserve the same environmental protection as Earth? Should we preserve Martian landscapes in their pristine state? Or is transforming them for human habitation acceptable? The concept of terraforming, deliberately altering Mars' atmosphere and climate to make it more Earth-like, crystallizes these tensions. Some envision a future where Mars possesses breathable air, liquid water on its surface, and thriving ecosystems transplanted from Earth. This would require centuries of effort and planetary-scale engineering, but it may be physically possible. Proponents see it as the ultimate expression of human creativity and ambition, transforming a dead world into a living one. Critics object on multiple grounds. If Mars harbors indigenous life, even microbial life, terraforming could destroy it before we fully understand it. We would be committing extinction on a planetary scale, eliminating the only other example of biology we have ever encountered. Even if Mars proves lifeless, some argue that its stark beauty deserves preservation. Just as we protect wilderness areas on Earth from development, perhaps we should protect Mars from human alteration. These debates will intensify as Mars settlement becomes reality. The decisions we make or fail to make will shape the planet for geological timescales. Future generations will inherit whatever we create or destroy. The responsibility is staggering. Art and literature have long anticipated these transformations. Science fiction writers have imagined Martian colonies for over a century, exploring every conceivable variation of how humans might adapt to and reshape the Red Planet. Kim Stanley Robinson's Mars trilogy, Red Mars, Green Mars, Blue Mars, traces centuries of colonization and terraforming, examining political, social, and ecological dimensions with extraordinary depth. Ray Bradbury's The Martian Chronicles approaches Mars more poetically, exploring colonization as a mirror reflecting human hopes and failures. Andy Weir's The Martian focuses on immediate survival, demonstrating how ingenuity and determination might overcome the planet's hostility. These works are not merely entertainment, they are thought experiments, explorations of possibility space, rehearsals for futures we may actually inhabit. The scientists and engineers designing real Mars missions have often been inspired by science fiction. Many cite childhood reading as the spark that ignited their passion for space. The cultural imagination precedes and shapes the technical reality. Music, visual art, and other creative forms will similarly evolve as Mars becomes tangible rather than theoretical. What songs will Martian settlers sing? What paintings will they create inspired by landscapes no Earth artist has ever witnessed firsthand? What new art forms might emerge from the unique conditions of Martian life? Low gravity, enclosed habitats, rust-red horizons, stars undimmed by atmosphere? The first generation of Mars settlers will carry Earth culture with them, preserved in digital libraries and personal memories. But subsequent generations born on Mars will create something new. They will develop Martian idioms, Martian humor, Martian aesthetics shaped by experiences their Earthbound ancestors cannot fully share. Over centuries, a distinct Martian culture will emerge, related to Earth culture, as American culture relates to European, or as Australian culture relates to British, but perhaps more divergent still given the greater separation. Language itself may evolve. Isolated populations develop dialects, then distinct languages over generations. Martian communication delays with Earth, ranging from 3 to 22 minutes each way, will limit real-time interaction, encouraging Martian communities to develop internal communication patterns. New words will emerge to describe uniquely Martian phenomena. Old words will shift in meaning. Eventually, Martian speech may become difficult for Earth speakers to understand without study. This linguistic divergence raises practical concerns. Scientific collaboration requires shared vocabulary. Economic transactions require mutual comprehension. Political negotiations require precise communication. As Martian language drifts from Earth norms, these activities become more challenging. Perhaps translation technologies will bridge the gap. Perhaps deliberate efforts to maintain linguistic unity will slow divergence. Perhaps Martians and Terrans will simply accept increasing mutual incomprehensibility as the price of separation. The psychological evolution of Martian settlers may prove even more profound than cultural shifts. Humans are remarkably adaptable, but we are also shaped by our environments in deep ways. Children who grow up never experiencing Earth's gravity, never seeing a blue sky, never feeling rain on their faces, how will their minds differ from ours? We have no way to know in advance. We can only observe and learn as the experiment unfolds. Some psychologists worry about the effects of enclosure. Martian habitats will necessarily be sealed environments, pressurized against the near vacuum outside. Colonists will spend most of their time indoors, venturing onto the surface only in cumbersome suits. This constant enclosure, year after year, generation after generation, might produce psychological effects we cannot anticipate. Agoraphobia might become the norm rather than a disorder. the concept of outside might become abstract, almost meaningless. Others are more optimistic. Humans have thrived in diverse and challenging environments throughout history. Arctic tundra, desert oases, remote islands, underground cities. We adapt. We find meaning and joy in circumstances that seem unbearable from outside. Martian settlers, committed to their new world, may discover fulfillments inaccessible to those who remain on comfortable Earth. The very challenges that seem daunting may become sources of purpose and identity. The question of Martian governance looms large. Who makes decisions for a Martian colony? Initially, sponsoring nations or corporations will likely maintain control, but as settlements grow and generations pass, demands for self-governance will inevitably arise. The history of colonialism on Earth provides cautionary tales: exploitation, rebellion, independence movements, post-colonial struggles. Can we learn from this history and avoid repeating its mistakes? Some proposals envision Mars as international territory, governed by multinational agreements similar to those managing Antarctica. Others suggest that the first successful settlers will establish precedents that shape all future governance. Still others argue that Martians should determine their own political structures without Earth interference, that attempting to impose Earth governance on Mars perpetuates a colonial mindset inappropriate for a new world. The Outer Space Treaty of 1967, which forms the basis of international space law, declares that celestial bodies cannot be claimed by any nation and must be used for the benefit of all humanity. But this treaty was drafted when Mars colonization seemed impossibly distant. Its provisions may prove inadequate for the complex realities of permanent settlement. New legal frameworks will need to emerge, negotiated among spacefaring nations and perhaps eventually including Martian representatives. Economic questions are equally complex. Who owns Martian resources? If a company invests billions in extracting Martian minerals, do they own what they extract? Can they sell Martian land to settlers? The legal ambiguities could stifle investment or, alternatively, create a lawless frontier where the powerful exploit the weak. Getting the economic framework right, balancing incentives for development against protections for fairness, may determine whether Mars becomes a utopia or a dystopia. These cultural, philosophical, political, and economic dimensions are inseparable from the technical challenge of reaching Mars. The journey is not merely about rockets and trajectories. It is about extending human civilization to a new world and determining what kind of civilization we will create there. The choices we make in the coming decades will echo across centuries, shaping the lives of countless future beings we will never meet. Why should we undertake this immense effort? Why spend hundreds of billions of dollars, risk human lives, and dedicate generations of work to reaching a cold, barren, radiation-soaked world 50 million kilometers away? The answers are multiple, and different people weight them differently. Let us examine the major arguments for Mars exploration, acknowledging both their strengths and their limitations. The survival argument may be the most compelling from a purely logical standpoint. Earth, for all its beauty and hospitality, is vulnerable. Asteroid impacts have caused mass extinctions multiple times in our planet's history. The dinosaurs dominated Earth for over 160 million years before a single bad day erased them. Supervolcanic eruptions, nearby supernova explosions, gamma-ray bursts, runaway climate change, engineered pandemics, nuclear war, artificial intelligence catastrophes. The list of existential risks is long and growing. As long as humanity exists on only one planet, we remain vulnerable to extinction from any sufficiently large catastrophe. Establishing a self-sustaining colony on Mars, one capable of surviving even if Earth became uninhabitable, provides insurance against such scenarios. It does not guarantee survival, but it dramatically improves our odds. A species spread across multiple worlds is far harder to extinguish than one confined to a single fragile sphere. Critics of this argument note that the resources required for Mars colonization might be better spent addressing existential risks directly, preventing asteroid impacts, reducing nuclear arsenals, developing pandemic preparedness, ensuring AI safety. Why build a backup civilization when we could instead protect the original? This critique has merit, but it presents a false dichotomy. We can pursue both strategies simultaneously. Indeed, the technologies developed for Mars exploration, closed-loop life support, radiation shielding, sustainable agriculture, may prove valuable for surviving catastrophes on Earth as well. The scientific argument for Mars exploration is also powerful. Mars preserves a geological record that Earth has largely erased. Plate tectonics, weathering, and biological activity have recycled Earth's ancient crust, destroying evidence of conditions during the first billion years when life emerged. Mars lacks plate tectonics. Its geological record extends much further back. By studying Martian rocks, we can learn about conditions in the early solar system that shaped both planets. The question of Martian life, past or present, represents perhaps the most profound scientific mystery within our reach. If we discover that life arose independently on Mars, we learn that life emerges readily given appropriate conditions. This would suggest that the universe teems with life, that biology is a cosmic inevitability rather than a freak accident. If we search thoroughly and find no evidence of Martian life, we learn that life's emergence may be rarer and more precious than we assumed. Either answer transforms our understanding of existence. Human explorers can conduct scientific investigations far more effectively than robotic probes. The Curiosity rover has traveled less than 30 kilometers in over a decade of operations. A human geologist could cover that distance in a single day, selecting samples with intuition and expertise no robot possesses. The scientific return from even a single crewed mission would likely exceed decades of robotic exploration. For those who value knowledge for its own sake, this justifies enormous investment. The technological argument emphasizes spin-off benefits. The space program has historically generated innovations that transform daily life: memory foam, water purification systems, miniaturized electronics, medical imaging technologies, and countless others. The challenge of keeping humans alive on Mars will drive advances in energy storage, food production, materials science, medicine, and artificial intelligence. These technologies will find applications far beyond spaceflight, potentially improving billions of lives. Some economists question whether this approach is efficient. Perhaps directed research into specific technologies would yield faster progress than the indirect stimulus of space exploration, perhaps. But history suggests that ambitious challenges inspire creativity in unpredictable ways. The Apollo program did not aim to create better computers, but the demands of space navigation drove computing advances that reshaped civilization. Mars exploration may catalyze breakthroughs we cannot currently anticipate. The inspirational argument appeals to less tangible but equally real human needs. We are a species that thrives on challenge, that finds meaning in striving toward distant goals, that needs heroes and horizons. The decades following Apollo saw declining public interest in science and engineering, at least until recent years, when private space ventures reignited enthusiasm. Mars exploration could inspire a generation to pursue careers in STEM fields, to believe that great accomplishments remain possible, to dream of futures beyond the mundane. This argument is difficult to quantify but should not be dismissed. Human motivation matters. Societies that believe in their capacity for greatness achieve more than those mired in cynicism or complacency. The symbolic value of Mars exploration, proof that we can still unite around ambitious goals, that we have not surrendered to short-term thinking and petty divisions, may justify investment even if the direct benefits prove modest. The economic argument looks further ahead, envisioning Mars as a source of resources and a market for goods. Martian minerals might someday supplement Earth's depleted reserves. Martian industries might manufacture products difficult or impossible to create on Earth. A Martian economy might grow to rival Earth's over centuries, creating vast wealth and opportunities. This argument is the most speculative. Current launch costs make importing anything from Mars economically absurd. It would be cheaper to synthesize materials on Earth than to ship them from another planet, but costs may fall dramatically as technology improves. And some resources, certain rare elements perhaps, or products of uniquely Martian conditions, might eventually command prices justifying interplanetary trade. We cannot know in advance which economic visions will prove realistic. The philosophical argument transcends practical considerations entirely. Some argue that exploration is intrinsically valuable, that understanding the universe is a worthy end in itself, regardless of material benefits. Others frame it in terms of human destiny or cosmic purpose, that we are meant to spread outward, that confining ourselves to Earth wastes our potential, that the universe exists to be known, and we are the instruments of that knowing. These arguments cannot be proven or disproven. They reflect values and worldviews rather than empirical claims. For those who resonate with them, they provide the deepest motivation for Mars exploration. For those who do not, they may seem like mysticism dressed in secular language, but values ultimately drive human action. The practical arguments may secure funding and public support, but the philosophical arguments inspire the pioneers who dedicate their lives to making it happen. Against all these arguments stand counter-arguments that deserve serious consideration. The money spent on Mars could address urgent problems here on Earth: poverty, disease, climate change, education. The lives risked belong to real people with families and futures. The resources consumed could be directed toward more certain returns. The timelines involved span generations, making accountability difficult and outcomes uncertain. These objections are not trivial. Hundreds of billions of dollars could save many lives if directed toward proven interventions like malaria prevention or clean water access. The opportunity cost of Mars exploration is measured in human welfare foregone. Advocates must grapple honestly with this trade-off rather than dismissing it. One response is that the choice is not binary. Global wealth is vast enough to pursue Mars exploration while also addressing terrestrial problems. Space exploration budgets represent a tiny fraction of global GDP, less than governments spend on countless less visionary endeavors. The question is not Mars or Earth, but how do we allocate our enormous collective resources wisely? Another response emphasizes the long-term perspective. Investments that seem extravagant today may prove essential for future generations. Our ancestors invested in cathedrals they would never see completed, universities whose graduates they would never meet, infrastructure whose benefits would accrue to descendants centuries hence. We are the beneficiaries of their long-term thinking. Do we not owe the same to our descendants? Perhaps the most honest response acknowledges uncertainty. We do not know whether Mars exploration will prove worthwhile. We cannot calculate the expected value with precision. We are making a bet that pushing our boundaries, expanding our presence, seeking knowledge and adventure beyond our home world will somehow, in ways we cannot fully anticipate, prove valuable. This is the same bet humanity has made countless times throughout history, sometimes winning spectacularly, sometimes losing painfully, but always moving forward. The journey to Mars is not a single decision, but a cascade of choices extending across decades, each step developing new rockets, testing life support systems, conducting robotic precursor missions, training astronaut candidates, building international partnerships represents an opportunity to reassess and adjust. We are not committing irrevocably today, we are beginning a process that future generations will continue, modify, or abandon based on what they learn along the way. This incremental approach reduces risk while preserving optionality. If Mars exploration proves less valuable than hoped, we can scale back. If it proves more valuable, we can accelerate. The key is to begin, to take the first steps that make subsequent steps possible, to build momentum and capability, to transform Mars from a distant dream into an approaching reality. The question we began with seemed simple. How long does it take to travel to Mars? The answer, we discovered, is anything but simple. It depends on orbital alignments, propulsion technologies, mission architectures, and definitions of what travel to Mars even means. But if we must provide a number, the current realistic answer is approximately 6 to 9 months for the transit, embedded within a total mission duration of roughly 2.5 to 3 years. This duration is not arbitrary. It emerges from the fundamental geometry of the solar system, the positions and velocities of two worlds orbiting a common star, combined with the limitations of our current propulsion technology. We cannot simply point a rocket at Mars and fire. We must dance with celestial mechanics, launching at precise windows, following curved trajectories that minimize fuel expenditure, arriving when the planets align favorably for eventual return. The journey itself is merely one challenge among many. Astronauts must survive radiation exposure that accumulates throughout the mission, threatening cancer and cognitive decline. They must maintain physical fitness despite months in microgravity, fighting the bone loss and muscle atrophy that afflict all long-duration space travelers. They must preserve psychological stability during years of confinement with a small group, isolated from Earth by communication delays that make real-time conversation impossible. Upon arrival, they must land safely on a world whose thin atmosphere complicates deceleration, whose surface conceals hazards, whose environment offers no forgiveness for error. They must establish a functional habitat, maintain life support systems, conduct meaningful exploration, and somehow extract or manufacture the propellant needed to return home. They must remain healthy and functional for 18 months on a planetary surface that actively seeks to kill them through cold, radiation, toxic dust, and unbreathable atmosphere. The return journey repeats many outbound challenges complicated by the physical and psychological toll of all that preceded it. And upon finally reaching Earth, astronauts must readjust to a gravity their bodies may have partially forgotten, reintegrate into a society that continued without them, process experiences that no other humans have ever shared. This is the reality of Mars travel as we understand it today. It is not a weekend trip. It is not even comparable to the Apollo missions, which now seem almost quaint in their brevity. A Mars mission represents the most ambitious undertaking in human history, a journey that will test every aspect of our technological capability and our human resilience. And yet we will do it. Perhaps not in the next decade, perhaps not even in the next 2 decades, but eventually, almost certainly within this century, human beings will stand on Martian soil. The momentum is building, the technologies are advancing, the will is coalescing among both governments and private enterprises. Too many people have dreamed this dream for too long to abandon it now. The first footsteps on Mars will belong to individuals whose names we may not yet know. Perhaps they are children today, growing up fascinated by rockets and planets, not yet realizing that their childhood obsession will carry them to another world. Perhaps they are young engineers or scientists currently working on precursor technologies, unaware that their contributions will prove essential. Perhaps they are already selected as astronaut candidates, training for missions that will eventually extend to Mars. Whoever they are, they will carry the hopes of our entire species. Their footsteps will echo across history, joining those of every explorer who ever ventured beyond known horizons, the first humans who left Africa, the first sailors who crossed oceans, the first mountaineers who summited unconquered peaks, the first aviators who conquered the sky, the first astronauts who escaped Earth's atmosphere. Each generation extends the boundary of the possible. This generation, or perhaps the next, will extend it to another world. But we must be careful not to romanticize excessively. Mars exploration will not solve humanity's problems. It will not end poverty or war or injustice. It will not automatically unite our fractious species or usher in an era of enlightenment. History teaches that exploration often exports existing conflicts rather than transcending them. The colonial era brought both wonder and atrocity. Space exploration could follow similar patterns if we are not deliberate about preventing them. The Mars we create will reflect the humanity that creates it. If we approach the endeavor with wisdom, cooperation, and ethical commitment, we may build something genuinely new, a society that learns from Earth's mistakes, that prioritizes sustainability and justice, that represents the best of human potential. If we approach it with the same short-sightedness, greed, and tribalism that have plagued terrestrial civilizations, we will merely replicate our failures on a new world. This is why the cultural and philosophical dimensions we explored matter as much as the technical ones. The rockets will work, or they will not. The life support systems will function, or they will fail. These are engineering problems with engineering solutions. But the question of what kind of civilization we build on Mars, that is a human problem requiring human wisdom. And we must begin developing that wisdom now before the technical capabilities outpace our ethical frameworks. I have taken you on a long journey through these pages, Josue. We have contemplated timelines measured in months and implications spanning millennia. We have examined the physics of orbital mechanics and the psychology of isolated crews. We have considered budgets in the billions and questions that transcend all material calculation. Mars travel, it turns out, is not merely a technical subject. It is a lens through which we can examine what it means to be human, our capabilities and limitations, our dreams and fears, our place in a cosmos vast beyond comprehension. The 6 to 9 months required to reach Mars may shrink as technology advances. Nuclear propulsion, if developed, could cut transit times significantly. Fusion drives, if ever achieved, could reduce them further still. Technologies we cannot yet imagine may someday make the journey trivial, a commute rather than an odyssey. Our distant descendants may look back at our era's Mars missions the way we look back at Magellan's circumnavigation, admiring the courage while marveling at the primitiveness. But that future depends on choices we make today. Every investment in space technology, every educational program that inspires young scientists, every policy decision that supports exploration contributes to a trajectory that could lead to humanity becoming a spacefaring civilization. Alternatively, every disinvestment, every cutback, every decision to prioritize only immediate returns could foreclose possibilities that would otherwise flourish. We stand at a hinge point in history. The next few decades will determine whether humanity remains confined to a single vulnerable world or begins its expansion into the cosmos. The technical barriers are surmountable, the resources exist. The question is whether we possess the collective will to marshal them toward this extraordinary goal. I believe we do. Not because I am naive about human limitations. Our history provides abundant evidence of short-sightedness and self-destruction, but because I also see the opposite tendency, the capacity for vision that extends beyond individual lifetimes, for cooperation that transcends tribal boundaries, for sacrifice in service of goals we may never personally witness achieved. These capacities are equally human, and they have driven every great accomplishment our species has ever realized. Mars awaits. It has waited for billions of years, circling the sun in patient silence, its red deserts and towering volcanoes unseen by any conscious eye, until our telescopes turned toward it. Soon, in cosmic terms, very soon, those deserts will feel the pressure of human footsteps. Those volcanoes will be climbed by human explorers. The silence will be broken by human voices. And when that happens, everything will change. Not immediately, not dramatically in the moment, but profoundly over time. A door will open that can never be closed. Humanity will become something new, not just inhabitants of Earth, but citizens of the solar system, participants in a cosmic story whose next chapters we cannot imagine, but whose first pages we are writing now. The journey to Mars takes 6 to 9 months. The journey to becoming an interplanetary species will take generations. But both journeys have the same beginning, the decision to start, the commitment to continue, the faith that the destination justifies the difficulty of the path. That journey has already begun. The robotic scouts have been sent, the technologies are being developed, the dreamers are dreaming, and the engineers are engineering, and the astronauts are training. Somewhere, right now, someone is working on a problem whose solution will prove essential for keeping humans alive on Mars. Somewhere, a child is looking up at the night sky and wondering what it would be like to stand on another world. That child may be the one who eventually does it, and when they take that first step onto Martian soil, they will carry all of us with them. Every scientist who contributed knowledge, every engineer who solved problems, every taxpayer who funded research, every teacher who inspired curiosity, every storyteller who kept the dream alive. Mars exploration is not the achievement of individuals, it is the achievement of a species. We are that species, flawed, fragile, finite, but also capable of wonders that transcend our limitations. We have walked on the moon, we have sent our machines to the outer reaches of the solar system. We have peered back to the beginning of time and outward to the edges of the observable universe. Reaching Mars is not beyond us. It is the next step on a path we have been walking since the first of our ancestors looked up and wondered. But how long would it take us to leave the solar system? If you are curious, check out the video at the left side of the screen. In this video, we reveal the crushing physics, biological barriers, and engineering impossibilities that make interstellar travel virtually impossible, even with future technology. See you there.